Looks like we're just about there. Welcome back, everyone. Looks like we can officially start. Congratulations is in order. First of all, we're finally at midterm week, so we're getting ready to cross the halfway mark. Congratulations, folks. For what we've got going on this week, we have our quiz 4 that's due next class. I'll be posting a quiz 5 at the end of this week, but probably the more pivotal announcements are we have our second exam. Not going to be on midterm week. We're going to put this one on just the week right after. Hopefully that makes midterm week a little bit less rough for all your rest of your classes. And as far as the coverage goes on this exam, it's going from section 2.5, the one we left off on exam 1, up to section 3.3, the basic differentiation formulas. We're not putting section 3.4 on this exam since we're finishing it out this week. Well, any questions at all, folks, with the announcements so far? Okay, well, we're getting our way through chapter 3 as well. We have section 3.4, 3.5 lined up for our work this week. Well, I might put in the next section just in case we don't run out of material. But for next week, I have the coverage listed out. The policies on this exam are exactly the same. It's Open Calculator. It doesn't have to be exactly those two, even though I said it's those two allowed on the exam. The major thing we're excluding is a graphing calculator. So as long as it's a basic calculator, you're all set. The formula sheet is going to be the last page provided on the exam. So it's going to be this page right here. You'll have basic theorems about continuity, a theorem right here to help us use the definition of the derivative, and then a table of differentiation formulas. Kind of weird. This one, f times g prime, the product rule, and this one, f divided by g prime, the quotient rule. Those didn't quite make it to the exam, but they're here just in case. So there's a couple things that are not completely needed. The rest of the material here, up to the last row of the table of differentiation formulas, are highly relevant to this upcoming exam too. As before, there's two versions of the sample exam. Version 1 is brand new problems. Some of them are a little bit more challenging that wouldn't really work on a real exam, but it's still a good study guide. And sample exam problems version 2 are just problems right out of the digital textbook. So these are pretty decent problems to practice with. They're primarily or almost exclusively odd problems, so you can check your answers as well. Well, I think that's my full set of announcements, folks. Any questions about the upcoming exam or the other announcements? Okay, well, I should have talked about, I think, everyone this morning about their testing centers. Some people are testing in the Idaho Falls Testing Center, and I sent you a link to schedule your exam. For the people who are testing in the Pocatello Testing Center, I sent you a phone number. They do it a little bit differently. You're pretty much just calling to schedule your exam. It's officially on Wednesday, October 16th, which means we won't have an actual class that day. We'll still have a Monday's class. Wednesday's class is really exclusively for the exams, and that's just in case people can only schedule their exam at, say, 2 o'clock, the same time that class is held. But since this is a fully online class, if you schedule your exam anywhere between the 14th up to the 18th of that week, just next week, then you're going to be just fine. Any questions or comments whatsoever? Okay, well, let's take a look at where we left off. We're here in section 3.4, looking at the product rule and quotient rule, so we'll pick up right there. So back to section 3.4. And so 3.4 looks like we did one quotient rule. So let's start from there, just from thinking about this one from scratch. If you're differentiating this function, which is a ratio of two polynomials, and you can't easily simplify it, what's making this one hard to simplify is the denominator has two terms. All we really do is we take and copy the numerator into two locations, here and here. In the first location, that's where we're differentiating the numerator. So the whole 2x plus 1 just turned into a 2. Over here, 2x plus 1 actually survives, and it came over here copied in. After we handle the numerator, the denominator goes into three positions. It goes here copied. It goes down here where we differentiate on the far right term. So that's where we see the times 1, where it's copied, still just x plus 3. And it also goes into the denominator squared. So that's our whole format for quotient rule. After we took those two derivatives where the yellow primes are, we just got to that step by the red dot, and we're just algebraically simplifying it right at that stage. So that's how each one of the quotients rule go. Some of them are a little bit more challenging than the others, but we'll try out another one kind of like this one for a warm-up. Any questions, folks, on how we ran through part A last week? Okay, let's try it out all over again now for part B. So here's our brand new function, f of x equals e to the x divided by e to the x plus x. Oh, sorry, question first, Braden? Oh. You're not quite coming out too well, Braden. Sounds like there's some background noise going on at the same time. You could try out the chat if you'd like for the question, but just double checking. I didn't miss your question or anything, did I? Oh, no worries. Okay, let's give this function right here a try. And maybe before we do this one, let's maybe do a slightly related problem. Suppose instead of this function, you had a function that went g of x equals e to the x plus, how about, let's make it be e to the power 2x divide by e to the x. So very similar to our f of x function here, we're doing a warm-up problem g of x. And the reason for this one is there's always a good to think about whenever you're about to do a quotient rule. Do you really have to? On this one, we really need the quotient rule, and let's say why. Denominator has two terms. It cannot simplify. So on this one, we need the quotient rule. And that's an important observation since the quotient rule is a pretty big formula. If you can get out of not using it, then that's always the best step to take. On this one, the one we're about to do, the denominator is different. This one had two terms, e to the x plus x. But if this one has just e to the x and the numerator is something we can work with to simplify, this one we wouldn't need the quotient rule. So let's say here, no quotient rule is necessary. So let's differentiate g of x. First, we would write it out this way. E to the x divided by e to the x plus e to the 2x divided by e to the x. Here we're using ordinary equality, meaning we haven't actually differentiated yet. We're just simplifying the function. On the next step, we have that g of x is equal to 1 plus, when we go to divide over here, we just subtract the exponents. So take the 2x minus x, and you just get e to the x. Now this function is way easier to differentiate just from taking the action of dividing the e to the x through into the numerator. On this one, g prime of x, the prime is saying we are finally differentiating the function. It's going to be equal to 0 for the first term, plus the derivative of e to the x, which is itself. So watch out for these kinds of things. If you have a nicer denominator, no quotient rule is necessary. But this one, same trick is not going to work. Sure, we could divide e to the x here, get a 1, divide it here, get a 1, but now you have to also divide it here. X divided by e to the x is still a quotient rule, and now our function is just more complicated to work with. So this one we have to hit directly with quotient rule. Any questions at all, folks, before we launch into that one here? Okay. Quotient rule definitely deserves some organization. So I usually think in terms of the top function, e to the x, divide by the bottom function, e to the x plus x. Then finally, the quotient rule is written out this way. The derivative of f at x is first take e to the x, differentiate it. Now copy down the bottom, e to the x plus x. Subtract the numerator copied, so just e to the x in the numerator now. Sorry, the red dot is a little bouncy today. But then multiply that by the derivative of the bottom. So e to the x plus x prime. And let me fix that parenthesis over here. There we go. So that fills out the numerator. Then in the denominator, we have something to the power of 2. But the trick with the denominator is it's always going to be e to the x plus x. So whatever was your original denominator, it comes down to your new denominator just to a higher power, one higher power. So that's the setup of the quotient rule, folks. Again, all we really did was we took e to the x, copied it there, and there. We're just differentiating the first one, and e to the x plus x went into all the other terms. At this stage, all we're doing is working out the derivatives and then simplifying the fraction as much as we can. So to start off, we have our nice derivative of e to the x right there by the red dot is itself. So we just copy it in. Now next, copy an e to the x plus x minus e to the x. And I wanted to use color coding just to show where we did differentiate. So blue to blue just to say we differentiate that one. Everything else is black to say we're copying from the line above. Then the derivative of this one's not so bad. It goes in stages. There's two terms. So on the first term by the red dot, you get e to the x. Then you continue differentiating, move over, differentiate x. That'll be a plus 1. And now that derivative is done. Everything is just divided by e to the x plus x squared. At this stage, we pretty much have our answer, but we still need to simplify it. Tragically, some of these things do simplify, so there's a little bit of work to do even at that stage. But usually if this was, say, a real examination problem, at let's say out of 6 points maybe, even if you made a mistake simplifying, you've got 5 out of 6 points just getting to this spot right here. That's where the calculus ends, and now we're just simplifying algebraically. Any questions at all, folks, getting to this step? Okay, now for the simplification part, first thing we want to do is distribute e to the x into the group. And this always looks a little bit weird at first. When you take e to the x times e to the x, much like when we took e to the 2x divided by e to the x, there's an exponent law where we just subtracted the x's. Over here for multiplying, we use the exponent law where we add up the x's. So this would be e to the power 2x. So in our first distribution right here, we get e to the power of 2x. Distribute once more, here to here is x times e to the x. So plus x, e to the x. And then we just do it all over again. I want to use a special pencil for the next one. Here we're distributing an e to the x along with a negative sign. So on that first product, negative e to the x times e to the x, we get minus e to the 2x. And the last multiplication here to here, that's negative e to the x plus 1. So it's going to be negative e to the x altogether. And I said that weird. It's negative e to the x times a positive 1 is the better way to say that. Well, we got the whole numerator out. Now all this is divided by e to the x plus x to the power 2. We did all this work because there is a true cancellation. E to the 2x right here cancels with negative e to the x. And we just have now 2 terms left over. I don't think we can do much with these two. You could factor out e to the x if you like. That's now kind of a stylistic way of just formatting your answer. Oh, we got a chat. Jamie says, will the exponent laws be given for the exam? The exponent laws are not on the exam, but a good place to look just for a really quick refresher is going to be this right here, the exponent laws review material. So these are not provided on the actual exam, but this is a good one to go through just for the practice. And another one is the worksheet down below, I think for a lot of people, you might want to start out with the worksheet and just see how these go. If you get stuck on a spot, then you might want to look at the other document and see just how things go. So I think that these would be the major things to be prepared for. As far as the actual exam too, it's only going to be this formula sheet that's provided, which is going to be information about derivatives and continuity. Other questions at the moment? Okay. And I'm glad you asked that question, Jamie, since one thing that we notice a lot, especially in chapter 3, is more and more things about exponent just keeps on coming up. Part of that's because of the product rule, or excuse me, the power rule that just forces us to deal with exponents. But it's going to come up again in section 3.5 when we're dealing with the chain rule. Just maneuvering through exponents becomes a lot of what's going on. On a real examination, though, going to try not to put a whole bunch of problems that require tons of basic exponent law things. So it's not going to be too heavy to get through on a real exam. But with our problem we have so far below, looks like this is basically where we're going to leave our answer. And again, up to you if you want to factor out an e to the x in the numerator, but perfectly fine to leave it as x, e to the x, minus the e to the x divided by e to the x plus x power 2. Well, folks, we did it. That's our first derivative of the day. Any questions at all getting through that quotient rule? Okay, well, we're going to practice out some more quotient rules on these notes. I have a couple applications down below, so let's take a preview of what we're getting into. There's our part C down below. Then this is actually provided on the real exam, so we'll be looking at this table. And the whole purpose of example 3 is just to take another look at the product rule and the quotient rule over here for these kinds of weird type of problems. When we go further through, this will be our next application, just a tangent line equation. And a more honest application will be this one, dealing with power and voltage and all that kind of fun stuff from electrical engineering. So first, we're going to take a look at another product rule, much like the one we just did. The trouble with these kinds of rules, though, in calculus is one thing we're going to notice a lot more in section 3.4, 3.5 is that every single differentiation formula that we start to gather, they all interact with each other. And part C, this would be a problem where I'd say not a good exam problem at all. It's definitely okay as a quiz problem and as homework. The reason this is not a great exam problem is this involves a lot of differentiation rules all at once. It's going to involve the quotient rule because we're definitely dealing with a quotient. We have something divided by something and no way to simplify it. But it gets even worse. Right here in this denominator, let's just temporarily highlight it. We have a product, x times e to the x. Because of that, this problem requires the quotient rule and the product rule. This deserves an exclamation mark. And you know what, let's leave that highlighting right there just to say that part right there is what also requires a product rule all at the same time. So our setup on this one is going to have to be really, really careful. Let's see how that color coding combines. Yeah, it looks like yellow is just gone. Let's start off by just writing out g prime of x equals this all together. So I'm starting off with 4 parentheses in the numerator. Derivative symbols are easy to miss, but definitely don't forget to put those in. I'm going to differentiate a function here and a function here. Then for the denominator, a function to power 2. Following the color coding, the top function goes only in 2 positions. X plus e to the x here, where it's differentiated. X plus e to the x here, where it's just copied in. Finally, the last function goes in everywhere remaining, 1 minus x e to the x. In that first position, it's just copied. Over here, it's differentiated. And down below here, it's being squared, just meaning we're just going to copy it down mostly. 1 minus x e to the x. So that's our setup so far. We are done with the quotient rule. We just have to differentiate here. That one's not so bad. It's a sum rule. But we also have to differentiate here. That's where the product rule, once again, shows up. So that bit just on its own is a product rule. So far in this function, again, this one is a tough one. I think there's only one problem like this in the real homework where it's a little bit tougher along these lines. So if you run into that problem, this would be a good spot in the notes to come back to. All we've done so far is set up the quotient rule. Any questions, folks, to that stage? Okay, I would say because this problem is tricky enough, not a bad idea to go and work out this derivative just all on its own. So let me see if I can add some color coding to it. I'll just put a purple bracket to say we're going to deal with this one right here. So let's go down a line. 1 minus x e to the x prime. So let's work out to just this part right here. It's a big computation just on its own. If you were to differentiate all this, you first differentiate the first term, which is a constant at 1. The constant will go to 0, so this turns into 0 plus negative x e to the x prime. So really all I've done in this step is said, to take the derivative of 1. We get a 0 out on that. Take the derivative of negative x e to the x. Well, I just copied it in just to prepare for the product rule. We'll write the next steps down below. So this one's definitely a tricky one just to look at. Does that make sense to folks on that first step, differentiating that bracket? Okay, well, we've got it nailed down to just this. And it's an ordinary product rule, so the way it sets up, it's not too different than what we did in the numerator when we did quotient rule. So 4 parentheses as before. This time there's a plus in the middle. Think plus for product. That's a good way to keep these in line. 2 more parentheses, move the prime symbol over, and we play the same little game with the factors. The first factor is negative x, so it goes into the first spots, here and here. Second factor is e to the x, so it goes everywhere else, here and here. And now that's our derivative to handle. It's not too bad because derivative of negative x is negative 1. So it's negative 1 times e to the x plus, I should just drop the parentheses. Let me do that there. Let's go, instead of plus or minus x, let's just go minus x. Multiplying derivative of e to the x, that comes up a lot on these notes. That's just e to the x itself. This is pretty much simplified, but we can take negative 1 times e to the x and write it in as just negative e to the x minus x e to the x. So everything in that purple bracket there is turning into this here, negative e to the x minus x e to the x. So think of part C, whenever this happens, it's really 2 problems duct taped together through the fraction bar with a quotient rule and through that bracket there with a surprise product rule out of nowhere. Any questions, folks, so far? Okay, this one's definitely an adventure, but now we can kind of reconvene and plug in our results. So let's start by copying in g prime of x equals, we haven't differentiated this one yet because we were paying a lot of attention to the product rule over here. So differentiating this is just going to give us a 1 plus e to the x. Then from here, we're copying 1 minus x e to the x minus x plus e to the x. And here we're putting in, I'll keep it as a bracket just so we can see the substitution a little bit better. 1 minus x e to the x prime turned into all of that. Minus e to the x minus x e to the x. Then the whole thing is being divided by 1 minus x e to the x squared. It's kind of tedious copying that denominator every single step, but it's probably a good idea since I've seen on exams where people took a shortcut, didn't copy the denominator. Usually they would do it on their last step, but just simply forgot. So for me, copying the denominator every single time is helping me to forget to include it. Well, this one is just about done, but we have the same kind of problem as we did in our prior example. This is the derivative, but it simplifies. And when we go to chapter 4, we'll find out that this careful work of simplifying the quotient rule results really is worth it when we go to solve applied problems. So, as before, to simplify this, we're just going to FOIL this time, collect our like terms, and cancel them as necessary. So let's carefully multiply out since there's a lot of terms. Here to here is going to be a 1. Multiplying here to here is going to be minus x e to the x. Then we change our arrows and distribute the e to the x into the group. So here to here is plus e to the x. And here to here, we're going to have minus x. E to the x times e to the x, shorthand is just e to the 2x. So that's our first distribution. This one's a little bit more annoying because of the extra negative sign right there. But there is a strategy. You could take this negative sign, distribute into this group, flipping them both positive, and then there'd be a plus right here. That's just shorthand, really. So if you like to save an extra step, that's a good thing to take. It makes the notes really hard to read, so I'm going to do it this way. I'll just distribute the negative on the next step. Go minus, a parenthesis, and just start foiling the parenthesis with the bracket here to here. We'll collect the results down below. So new distribution, here to here is going to be minus x e to the x. And here, multiplying here, is going to be minus x squared e to the x. Distributing this way, let's see, we have e to the x times negative e to the x. So that's going to be negative e to the 2x. And last one, we're getting through this problem. That last multiplication is e to the x times negative x e to the x. So it turns into negative x e to the 2x. So one big fraction in the numerator. Denominator is 1 minus x e to the x squared. So my next step is to distribute the negative sign in and collect our like terms. So here we go. It starts off with a lot of copying up to where the red dot is. 1 minus x e to the x plus e to the x minus x e to the 2x. And distributing the negative sign into that group just means we're multiplying everything by -1, which just means we're flipping all the signs. So this will turn into plus x e to the x plus x squared e to the x plus e to the power 2x plus x e to the power 2x. Hopefully they're all there. Let me know if I dropped a term. To me, that's the most easiest mistake to make when there's just so many terms you're accounting for. It's easy for my eyeball to just miss like a term in the middle, for example. Then down below, 1 minus x e to the x squared. So this is the fun part. This is going to tell us, was it even worth foiling these two out and these two out? If there was no cancellations, I'd say probably not, but we do have a cancellation here or there, I think. Let's see. There's a negative x e to the x combining with positive x e to, no, that's not the right one. This one has 2x, so that's not the like term. It would combine with that one. It has x and e to the x, both to the same powers. So that's got to be a little bit careful canceling these things. And what else do we get? Negative x e to the 2x. Oh, they do have an opposite. This one and this one do cancel out. Those two would be like terms. I think we've gotten just about everything else. The only survivors are here, here, and here. I'm circling them so I don't lose track of them. So the derivative g prime of x, all said and done, is 1 plus e to the x plus x squared e to the x plus e to the power 2x all divided by 1 minus x e to the x power 2. Well, we did it, folks. I think this one is a pretty nasty problem. And the reason we did this one today was just to show how it goes if it ever comes up in the homework. I don't think we can zoom out to show the whole problem. Let's just zoom to this stage. So I have one that goes about like this in the homework where it is a quotient rule combined with a product rule. And these are the kinds of things that you have to do to get through those sort of problems. They are pretty long and tedious, but again, this would never be an exam question. Think of this problem as more just a challenge question in the homework where we're trying to understand how to set up quotient rule and survive a product rule all at the same time. Any questions or comments at all, folks, getting through this one? Okay, well, at this stage, we did our major work dealing with the product rule and the quotient rule. And again, I just have a few problems at the end of the notes where we're practicing some of the results a little bit further and looking at applications. So here, again, is our table of differentiation formulas. This is on the last page of the exam. And it's a pretty nice set of formulas. It's a reminder that the derivative of a constant is 0. You have the power rule here. That one, you might have noticed we use a ton. So same with this one as well. The derivative of e to the x just being e to the x. The results down below are things that we essentially are taking for granted every time they come up. If you have a constant times a function and you take the derivative, you just have the constant times the derivative of the function. Then the good old sum rule, the difference rule, we've used a bunch. The only thing that's on here that's not directly going to be used on exam 2 are these two. But it just so happens in the notes section 3.4, those are the ones we're practicing here and now. So here's how it goes. These are really weird problems because they don't even tell us what the function f and g even are, and they suddenly want us to take the quotient rule of f and g evaluated at 3. Really, the major purpose of example 3 is just practicing these two rules, quotient rule and product rule, one more time. So we have several evaluations on the function. Notice one of them here, f of 3 is -4. That's an ordinary function evaluation. But this one is f prime at 3 equals 2, so that one is giving us the derivative. It's saying the slope at x equals 3 of the tangent line is a slope of +2. And similarly for the g function, we have an evaluation and a derivative at g. So now we want to take the derivative of f divided by g and evaluate it at 3. Really, we're just doing this once again, and it comes together in this way. It doesn't hurt to color code it. So there's our top function f in blue, our bottom function g in green. When we go to write this out, this turns into first f prime at 3 times g at 3. Sorry, my color coding is a little bit trickier than I thought. There we go. We put a minus in the numerator if it's a quotient rule, and then go f at 3 multiplied by g prime at 3. And then the total result is divided by g at 3 quantity squared. So that's the first step of a pretty strange problem like this. Essentially, all I've done is put at 3 using this formula every time a f or a g appeared, or its derivative. And now when we're looking at this, we have f prime at 3 here, g prime at 3 here, so we can start plugging in all of these values. Any questions, folks, with this setup with the quotient rule? Okay, pulling these in, we have for f prime at 3, that one was just a 2. Let me put in the fraction bar first. So here's 2 in place of f prime at 3. Next, for g at 3, that one is just an ordinary function evaluation. So we grab this value here. G of 3 is 5. Then minus, we'll do it all over again. This one is an ordinary function evaluation, f at 3. So we go to this part right here. f of 3 is -4. And finally, this one is a derivative, g prime at 3. So we'll go to this highlighted one where we get the value -4. All of it is divided by the quantity g at 3 squared. But that one is not differentiated, so we grab that function evaluation, just the 5. At this stage, all we're really doing now is just simplifying all the arithmetic. So that was the setup of the quotient rule on the left. This is pulling in the information from the row above. It is a little bit tricky, so watch out for the function values versus the derivatives when you do this one in the homework. Then finally, across the numerator, we'll have 10 minus 16. Its denominator is a 25. So the total result looks like this is going to be -6 25ths. And we did it, folks. That's the quotient rule when you're evaluating the functions at a particular number 3 in this case. That was so fun. We'll do it all over again, but with a product rule below. Any questions first on how this one goes through? Okay, just throwing down some color coding up here. The one below is now a product rule. And notice the reason we're doing both a product rule and quotient rule in this problem is because the formulas really are very, very similar. A good way to kind of understand these is you can think of the quotient rule, the one on the right over here, as really being generated from the product rule where you make two changes. The plus sign becomes a negative sign, and the second change is you divide by the function squared. So the product rule below here would just say fg prime at 3 turns into f prime at 3 times g at 3 plus f at 3 times g prime at 3. So we're done with it. That's the quotient rule above. Next thing we do is we analyze our output here, grab the right function values, and just crank out our result. Any questions first, folks, with what we put down here? Okay, we're almost done with this one. So let's plug in our results. F prime at 3, we should be looking here by the red dot. That value gives us a 2. Then next step, G at 3. That one is this one, the one that's not a derivative. So we get a value 5. Plus in the middle. Now we're looking at f of 3. So we grab this value here, the -4. And last one, g prime at 3 is this -4 right here. So this one turns into, after cranking it out, looks like 10 plus 16 for a total value of 26. So we did it, folks. That's another look at the product rule, quotient rule together. I forgot to color code the start of this, but we're probably okay with that. Just would look a little bit different from here down to here. There's one just like this one in WebAssign. I wouldn't say this is a very common quiz or exam question, but again, the whole purpose of this example 3 is just to force us to look at the formulas again and kind of get better understanding of them. So definitely a weird problem, but any questions at all, folks, getting through example 3? Okay, well, with what we've got next, looks like we're looking into a tangent line equation style of a question. And that's this example right down below here. It says, find the equation of the tangent line to the graph y equals f of x at a given point 0, 0, where f is defined as this thing. Again, these are pretty challenging problems because, once again, in our numerator, we have x times e to the x. That's hard to highlight. But that means this one's going to be a quotient rule together with a product rule once again. So we'll analyze this one carefully and get the tangent line. Problems like these always go in kind of the same format. So a best way to start this one in steps is do this as your step 1. This is also a pretty tricky question in a certain sense, based on where we're at in the course. When it says the tangent line equation, A lot of people might be thinking of how we did it the very, very first time. Let's take a look at the notes just to show you what I mean. The very first time we did a tangent line equation problem was all the way back in section 3.1. We were still in September, wow. And in these notes, rather, when it said find the equation of the tangent line to the curve, we often just used that formula. That's all we had. We didn't have any differentiation formulas. So now the trouble is you only want to use that formula there if the instructions on the exam say using the definition of the derivative. On our upcoming exam 2, you'll have an equation or a question just like this one. It says find the equation of the tangent line to the graph and nothing about using the definition of the derivative whatsoever. That means we're just going to use our ordinary differentiation formulas to calculate this. We'll write f prime of x equals, organize our function as before, and start setting up the quotient rule. So the big punchline is, when you see this, the definition of the derivative is not needed, since we have better tools at our disposal for actually getting a tangent line equation. We really just needed the derivative to help us get the slope. Any questions about that so far, folks, before we jump into this one? Okay, well, let's write out the setup on this one very carefully as well. If it's a quotient rule, then you're going to have something differentiated multiplied by something else minus something multiplied by something differentiated, and then the whole thing divided by something to the power of 2. So that's our setup. Next step on the setup is just drop in the right functions. Xe to the x only goes in the numerator in the first placeholders. So it would be here and here to start us out. Let me try again on that one. Xe to the x. Then if you have the numerator position, the top function, settled, you'll know that x squared plus 1 goes everywhere else. That really helps with the memorization on this kind of problem. So x squared plus 1 goes here, here, and here. At this stage, we're just differentiating as normal. This derivative right over here by the red dot is no problem. That's just a 2x. That derivative, however, is a bit of a problem. That one requires a product rule. Because there's a product rule already baked into our problem, you might find it a good strategy to just separate this out, work out the product rule, and plug it back in. So let's go with that strategy one more time. I'm going to convert this to a purple parenthesis, just a way of conveying the substitution we're about to make. And let's take a look at x e to the x prime. The good news on this problem is I think this is a little faster one to get through. The product rule is not too bad. But like before, let's work it out carefully. Product rule sets up almost just like the quotient rule, like we mentioned. Here's one key difference. There's a plus in the middle. And no denominator is the other key difference. So if you're a fan of setting up these placeholders, it really helps our mind's eye of deciding where things actually go. So x goes into the first positions, here and here. E to the x goes everywhere else. So that's our setup differentiating that part right there with product rule. Any questions to this stage, folks? Okay, working this one out, it goes pretty quickly. Derivative of the x right there by the red dot is just going to be a 1. So now we have 1 times e to the x plus x. So I've copied the e to the x plus all the way to x. Now derivative of that e to the x is another e to the x. That comes up a lot in these notes. We'll have more different functions once we get the chain rule and logarithmic functions in the further sections. But for the moment, e to the x seems to come up quite a bit whenever it's a product rule or a quotient rule. So now below, this is pretty much in simplified form, but we can say 1 times e to the x is just e to the x plus x e to the x. So that's what's going to copy right up here through the product rule. So let's rewrite our derivative. F prime of x is now equal to, where the purple parentheses are, let's keep them purple still and go e to the x plus x e to the x. Now, the rest is copying until we get to here. So x squared plus 1 minus x e to the x. Then finally, derivative of x squared plus 1, right here by the red dot. Like we mentioned, this one is just a 2x. And denominator, still x squared plus 1 squared. Well, we did it, folks. That's our step 1. We calculated the derivative. I think that's the hardest step on this whole problem. Any questions, folks, getting to that stage? Okay, now that we're here where the red dot is, if we were in a prior problem where it was just differentiate with the quotient rule, we might have actually simplified that. Imagine FOILing this out, combining these two together, and trying to cancel like terms. But in this problem, that's actually not necessary. The reason is, all we want from this derivative is now just a slope. We're going to find the slope when x is 0, because the given point, the first coordinate is 0. Let's write here x is 0 that we're going to plug in. And we're just going to plug in 0 into this function right here. That's a faster way to go with this problem. So let's say now we're ready for a step 2. In step 2, we're getting something major. If we wanted the equation of the tangent line, then we absolutely needed the slope. To get the slope, the derivative is what tells us what it'll be at every value x, but we just need to know which x. We're plugging in 0 because of the supplied point. So putting all of that together, we can say m equals f prime add 0. So that was the slope of the tangent line at every x, where we say f prime of x. But now we're saying we want that one specific slope when x is 0. We can evaluate that. Everywhere there's an x, right here on the prior line, just put in a 0. So that's going to be e to the power of 0 plus, this is 0 times e to the power of 0, so I'll just put 0 there. This is 0 plus 1, so I'll just put a 1 there. Minus, because of that x, this is 0 times e to the power of 0 times twice 0. Let's just say 0. Then the denominator is 0 squared plus 1 squared. So we plugged a 0 there. But that's just a glorified number 1 exactly. Back over here, when we start to simplify this, e to the power of 0 is a 1. So we get 1 plus 0 times 1. That's just a 1 in the numerator. A 1 in the denominator. So finally, it tells us our slope is 1 altogether. And by the way, the power rule we just used, exponent rule, was e power 0 is 1. Or if you prefer, as a formula, a to the power of 0 is always 1, provided a is not 0 itself. So we did it, folks. That's our step 2. We now have a slope. Next thing we're going to do is just write out the point slope form for the equation of a line. Use the given point 0, 0 as our x1, y1, and our slope down here that we found in step 2. First, before we do that last final steps, any questions getting to this stage? Okay, well, let's put this together and make it happen. So here's our step 3. Let's grab and just consolidate. Slope m is 1. We had a provided point 0, 0, but that's just going to be x1 comma y1. The equation of the line is y minus y1 is slope m times x minus x1. So from down here, we're just plugging in information. Y1 is 0 and x1 is 0, so it's a pretty fast evaluation. It turns into y minus 0 equals the slope m, that's just a 1, times x minus 0. So the whole equation turns into just y equals x upon simplifying. That's kind of a massive simplification because the derivative looked like it was super complicated. But if all we're doing is plugging in a number, something big and nasty like that just turned into a 1 really quickly. Well, we did, folks. We have our tangent line equation. Any questions whatsoever getting there? Okay, well, looks like we have a good amount of time for our last problem of the day. If we have a little bit more additional time, we may start section 3.5, the chain rule, but I'm hesitant to do that since section 3.5 is pretty tricky. It's a good one to not break across two classes on the very start if possible. But our next problem is the applied problem. We're going to be, again, looking into applications like this one a lot more in the coming chapter, chapter 4. But this is another early start to just thinking about what the applications are and how to work with them. It says here, the power that a battery supplies to an apparatus, such as a laptop, depends on the internal resistance of the battery. So I believe them when they say that. I'm not very great at electrical engineering whatsoever, so I'm just going to take their word for this. They tell us next, for a battery of voltage V and internal resistance lowercase r, measured in ohms, the total power delivered to an apparatus of resistance uppercase R is given by this formula right here. So the power, again, imagine this power being supplied to your laptop through a battery. With voltage V, we'll have a V squared there, involves internal resistance, capital R, divide by R plus lowercase r. Oh, I said that wrong. R is just the resistance of the battery. Little r is the internal resistance of the battery. So that's all kind of interesting. But they make a big statement here, assuming that V and R are constant. So that's the uppercase V and the lowercase r. Those are just constants in this problem. We need to know that when we go to differentiate. It says calculate dP dr. Think of that as P prime whenever you see that. But because this is an applied problem, Leibniz notation dP dr is most preferred in this kind of setting. And you can kind of see why. There is 1, 2, 3, 4 different kinds of variables. R is in uppercase and lowercase, means it's two variables as well. This tells us P is the dependent variable and R is the independent variable. So we need to calculate the derivative of that thing. Looks like it's a quotient rule. And then give a practical interpretation of what the meaning will be for our result. Any questions at all, folks, before we begin with this one? Okay. Now, I just want to say, I feel like this problem here is a pretty tough problem. So if it feels like it's not something that you really are understanding fully the first time we do this, I wouldn't be too worried. This is kind of like a warm up. It's a preview for what we're doing in chapter 4 so that once we do get in chapter 4, all this stuff doesn't just seem like it's brand new. So if you're going to differentiate a function like this one by the red dot, a really good idea is work by analogy. And here's what I mean. This one is a really hard derivative because of all the unfamiliar symbols, but we can take this function and interchange it for something that's familiar, differentiate it as a warm-up, and then the derivative of the harder one will make a whole lot more sense. So here's the warm-up. We're going to define a new function, y equals, and we want to make it as similar as possible, but I'm using y instead of a p, and I'm going to use x instead of the uppercase r. Again, the uppercase R coming from here in Leibniz notation is one of the major things that it's telling us. That's the independent variable x. So up in the numerator is v squared, but v was supposed to be a constant. So let's just put in something like 25. The numerator involves r, but that's a variable, so we can think of that one as an x. Then down below, that big uppercase R here is also thought of as an x. Plus, lowercase r, however, that's a constant. So we'll put in something like, say, a 2. to power 2. So if we can differentiate to that function right there, then we'll use the same analogy to show how the derivative goes for the larger function. So that's our strategy whenever we're dealing with something like this that feels so brand new. Down below here, this derivative is not too bad. Let's set it up with a quotient rule just to be careful. Y prime will be equal to the derivative of the top. So here's 25x prime. Copy in the bottom, x plus 2 power 2. Then go minus the top, 25x. Take the derivative of the bottom, x plus 2. And I think I'm running out of space here. Let me not try to jam it in. Another try at this. X plus 2 squared minus 25x. I think I need a bracket here. And we're differentiating x plus 2 power 2. All of which is divided by x plus 2 to the power of 2. But that whole thing also has to be squared. So that's what the quotient rule would look like for this function here. Let's actually finish it off as well, just to get a good feel for how the larger question is going to go. So if we finish this one off, we need the derivative of 25x. That'll be just 25. That's going to be x plus 2 squared minus 25x. And notice the derivative of this one is a little bit different. That one's kind of a challenging derivative because it has a power 2, and the function has been factored as x power 2 to the power of 2. If we were to try to differentiate this, we could use the product rule because x plus 2 squared is x plus 2 times x plus 2. But using the product rule in something like that is kind of making a mountain out of an anthill. This one is a nice function to differentiate just normally. And the reason is, if you FOIL out that function, you get x squared plus 4x plus 4. So that's the result of FOILing x plus 2 times x plus 2. And then x squared plus 4x plus 4, differentiating that one is far, far easier. So in total, the derivative of x plus 2 squared, we're just differentiating that thing where the red line is, red dot I mean, and we get to 2x plus 4, all of which is divided by x plus 2. It's x plus 2 squared, but in this configuration, those two exponents would just multiply. So 2 times 2, 4 power of 4. So there's more you could do with this. It could potentially simplify a little bit more, but we're not going to try to simplify it too much. We just want to get to this stage to help us out when we're about to differentiate that function there. Any questions at all, folks, with the warm-up? Okay, so now here's what we're going to do next. Everywhere you see an x, think x is r. And everywhere you see a y, think y is p. Now we need to differentiate this function right here. So we're going to call this dp dr, where the denominator r is uppercase 1. We change that to r, we're not doing this derivative at all. So the uppercase r is telling us that that's the independent variable, much like the x. But it's also a quotient rule, so let's be very careful with this one, as we were with the other ones. It's going to set up this way. A parenthesis with a prime symbol, ordinary parenthesis, minus another ordinary parenthesis, and then one with a prime symbol. And then all below, we'll have something to the power of 2. So that's our setup to start this one out. Every quotient rule goes all the same kind of way. So v squared r will go into these two positions. Next, our denominator is r plus r. Plug it right here. Oh, excuse me, it's r plus r squared. Let me just put the power 2 there. I think that's an okay way to convey it. But I wouldn't necessarily want to plug it in right here. It's the same conflict that we had over squared derivative, it's much easier to just differentiate it once you expand it out. So let's see if we can do that. Well, let's not sneak in some extra space then. Maybe if we go here. Oh, it did move, but it doesn't help. Let's maybe just do it right here. R plus R power 2 turns into, when you FOIL this thing out in total, R squared plus 2 plus lowercase r squared altogether. So that will plug in right here, and then we'll differentiate it. But let me make that a little bit bigger. So inside plus 2, let me format it as little r, big R, plus r squared. And I just got a message, my internet is unstable. That's never a very good sign. Are you all hear me and see me at the moment? Did. Okay, awesome. Glad to hear that, Alejandra. It is cutting out for, must be an ISU network problem going on right now. Very strange. Oh, sorry to hear that, Jamie. I had a problem with power just last Thursday's class. Well, let's definitely make this our last problem for the day just because of internet issues, power instability. We've got a lot going on today, but we're going to get through it, folks. I promise. We'll make this our last question. Try not to rush through it just in case it gets a little bit glitchy and laggy at the end here. But what we've done so far is we've set up the quotient rule. Only extra step I took here by the red dot was I took r plus r to power 2, and that's the result of FOILing it out. So differentiation goes a little bit cleanly. But over here, it's better just to copy it in, r plus r power 2. I should say that right. It's uppercase R plus lowercase r to power 2. It's kind of annoying to have to say uppercase and lowercase each time, but it's worth it because it makes it clear. So first line here, that was just our setup. And now we're focusing on this, where the yellow is temporarily highlighting. That's a tough derivative, v squared r prime. But the way to think about it is it's no x prime. X is playing the role as r, and when we differentiate this thing, we just have the constant. So back over here, it's the same exact abstract constant, but we are told it's constant. It doesn't depend on r. So when we go to differentiate this thing, r is to power 1, so it's going to vanish. We'll just get v squared. So just v squared from this one here, again, much like following the highlighting in yellow, how the 25x prime just turned into the 25. Does that make sense, folks, on that first term there, differentiating? Minus v squared times. Again, it's not an easy derivative looking at that. Uppercase r is the variable, and the lowercase r's are the constant. For x squared, two r. So that 2r here two x r. When we differentiate this thing, that r power 1 will vanish. Oh dear, sorry to hear that, Alejandra. Sounds like I'm cutting out pretty badly at this stage. But you know what we could do is potentially talk and type. So let me say here on that 2R is 2R. At this step is right here, that lowercase r squared. Let's say here, case r squared is a constant. So if we go to differentiate that r squared, because we're told it's a constant here, it goes to just a 0. So let's say here, the derivative of r squared is 0. That means down below over here, and now that takes care of the numerator. Whole denominator is just so we did it, folks. That's our derivative. Looking at the form we had over here, it's very, very similar. But the tough thing about this one was to see what happens with the variables when your function is written in this way. We still want a practical interpretation. So let's say this is the rate of change for power. The value of R varies. Well, I think we got to the end, folks. Sorry for the trouble with the technology today. It looks like all sorts of problems are happening on your end and also on my end. Could potentially, but the Wi-Fi has been here pretty stable. Possibly what I might try next time is using a different computer that connects to the internet through a Wi-Fi, improve our stability. So I'll make a quick note of that and make sure that that happens next class so we don't have to worry about too laggy or missing information for that. Questions at all, folks, before we call it a day? I did not get that notification. That is really weird. Sending to a third party. That's possibly recording. Let me type that out here in case it's lagging a bit. That might YouTube Live recording the class. I don't know for certain, but I think that's the likely suspect. But any other questions at the moment, folks? Okay, well, we'll reconvene on Wednesday, hopefully a little bit more stable technology. I